do an IRT in R analysis. So an IRT is basically just gives you some details, but I'm just going to do a quick overview. There's a lot to the theory. It's important to kind of understand, but just for a quick overview, theory for how people respond to items, it has less items than classical test theory. Needed to be reliable, but you need way more participants than classical test theory. It's more complicated. And the latent variable score depends on the distance between items in IRT. This is more about pass, fail, yes, no. It's a dichotomous thing. Now, there are IRTs that are not just dichotomous, but the one we're going through today, and the most basic one, is a dichotomous IRT. It's more accurate, and there's multiple parameters you can look at: A, B, 1, 2, 3, and 4 parameters. We're going to be looking at A, B, 1, and 2, but people do look at 3, but not all the time, and then like rarely do people look at 4. But 3 and 4 are more about guessing, and so IRT can be used for things like test validation, and that's kind of what we're going to be using it for today. So first we would load the data. Library, same way we're librarying it. IRT is the name. Read Excel. View IRT data. So we'd run that. Install packages if you need. So we can install it if we need it, but we do not. However, you probably will need to install some packages. We'll be using Psych and LTM. I'll be loading that up. Now there is going to be something kind of weird with how you're going to have to go about this. So the Psych package contradicts with another analysis we're doing soon with LTM. So you need this loaded to run the unit dimensionality, which is some way of testing if everything is on one component. And you're looking at one dimension, which is kind of an assumption of IRT. So either you can run this at the end after everything else you've done as a check, and that will prevent like this error from coming up that will happen, or you can just have 2 different projects going on, and I have the 2 different project solution to avoid the error, because it's ours sometimes like that. So we'll go through that later. But for now, just know that that's the thing that will be coming up. So we're running the unit dimensionality. Right here it says parallel analysis. So number of factors equals 2 and the components are 1. Sometimes when I run this, it geeks out. But I'll run it. But sometimes it geeks out, or it'll say something weird, but it should be 1. And sometimes it does that. But yeah. Now we're going to move on to the parameters. So what we did here is we made this thing called IRT mod, and we're loading in here. This is where we're making our IRT setup for the parameter set that we talked about earlier. LTM, we want to look at IRT data set. That's the data set up here named. And then Z1 says that we have one latent variable we're predicting. IRT.param is true. So that basically means that we're looking at ABC format instead of slope-intercept, since we're looking at one parameter. Even though sometimes when I run this as components 2, I know that this theory is 1. It runs multiple times. It flips between the 2. But I know how this measure is made personally with this data. And so I know it's a 1, but do keep that in mind. Sometimes run it a couple times to make sure you get the same results. Then here we go, breaks the items down by difficulty first and then discrimination. So I'll run that summary. So here we get kind of a summary of all of the things we see. We see it goes difficulty, discrimination down here, coefficients, the method of how they're doing it, the quadrant points, all that kind of stuff. Now, if we run it as coef, all that basically does is it breaks it down by difficulty and discrimination side by side, so we can kind of understand the data a little bit better. Now I'm going to go over a little more about what difficulty and discrimination are while they're side by side. So difficulty is the standard deviations from the mean, aka the z-score from the mean. Negative for difficulty means easy, and then positive is harder. So when we look at this, the easiest item is item 1. We're looking at difficulty and 8 because these are -2 numbers. That means they're pretty easy. And then the hardest item is item 3 that we have here because it's 1 positive. So it's 1 positive standard deviation in difficulty. And we're only looking at difficulty right now, this column. And then discrimination, above a value of 1 is ideal for discrimination. And we really want it to be between 1 and 4 with no negatives. That's what most of the literature supports. And all of them really are good except 8. 8's a little borderline because that one's 0.9, but the rest of these are above 1 and below 4. The best item here is item 6 because we do want it to be as close to 4 as possible with discrimination because that just means it discriminates more. Perfect. So now we're going to plot all the items at once in a ICC, which is an item characteristic curve. It helps us see more on these items. It's a mathematical expression, explains subject probability of success on an item. We really ideally want this S shape. This is because if you have more ability, you're more likely to get it right. See up here, probability, ability. So if you have more ability, like we said, the positives, these are like Z-scores out. So the more ability you have, the more knowledge you have, the higher the probability you'll get it right. So we want the number up here, but then we want people that don't know anything to not get it right. So we want it down here. And ideally, an ideal one would be like S, woo, and then whoop. That would be like an ideal, what we'd want. However, that's ideals. So we look at how much of an S and how much it falls under that to see how much we like an item based on an item characteristic curve. More ability, more likely to get it right. Less ability, less likely to get it right. You really want most of the theta you're interested at the time. So that means basically underneath here, like, do you want there to be able to rank them, or do you want to just yes, no them are correct, incorrect? So if we look at these, like some good S curves, 1 is horrible, 8 is horrible. These ones are not at all, right? This one looks more like slopey and fun, but it's not a good S as much because look right here. It's just this like slow buildup. It's a good one to use, but not perfect. I'd say the closest shape of an S that we like is 6, but it is 2 on the negative side because right here where pink is, if you look at 0, which is 50-50 chance. So basically 0 is like you got a 50-50 chance of getting it right. Like 50-50 chance of getting it right. Oh, like, not that much ability. Like, I don't really know, 50-50, but you're almost certain to get it right. That doesn't feel like it's discriminating that well. You know what I mean? But it's not horrible. It's just a little more, less ability people are more likely to get it right than total ability. It's kind of what that's saying. So if this was moved right over 0, it'd be perfect. So that means 6 is a good item, 2 is red, 4 is a good item, 5 is a good item, 7 and 3 right here. These ones are good items to some degree. Some are better than others, but they're all kind of an S thing, whereas 1 and 8, not good at all. Now you can also plot these individually. Like if I just wanted to, because this is a lot, right, on here. Let's say I want to look at just item like 7. Boom, just item 7. If I just want to look at item 2. So how I would do that is right here. I'll just go ahead and run them all, but so you can see like I got them all down. But what you're doing here is you're saying plot, because you want to plot something, open parentheses IRT mode, comma, equals type, equals parentheses ICC, parentheses closed, comma, items equals, so that's the curve you want to look at. 1, 2, 3, 4, which one? What item do you want to look at? So you're basically just like this one where you plot all of them. You're just making it specific items. And again, here, we're saying plot. We want to look at IRT mod that we created, which was right here, the parameters. Type, ICC, items. All right. So we've gone over that. Now we're going to look at the item information curve. I'm going to run that. So that's how you do all of them at once. So it's basically, this is a test information curve. It basically tells you where is the information of the test coming from. Like where's the most information coming from the test and what items. So this one breaks it down by items, the test information curve. So we can see that we're getting a lot of information from item 2 for people that have negative to the average ability right here. We can also see like, we're getting a little less there. We're getting a lot of ability on higher ability people from 7 and right here too. So you can see the amount of information you're getting. So it's kind of helpful to see the breakdown of where each item is giving the information to the test. We can look at this again, just like above for each item. So you do plot. IRT is what we're looking at, the parameters we're setting up. Type IIC, because we're looking at information curves, and then which item we want to look at. And up here again, plot, IRT mode, type ICC if we want to look at all of them at once. So we can do that, right? Woo! And we get all of them individually. And we can also see how the test just performs overall, right? So we saw each item breakdown, but when we aggregate all of those test items into one test information function, we can see where are we getting the most information for our test. And it looks like the most of our information on this test, the accessibility, is the lower negative to average people. We kind of see if they don't know anything more than the people that do know things. Our test is really good at figuring out, do you kind of not know your stuff? And that's where most of the information is at assessing. So this tells you, where you have the most information, what ability points being measured the most. You really ideally want a normal distribution. So this distribution is kind of like slightly targeted to the left. So it's not really ideal, but it's not a horrible test information function, but not perfect. Not really what we want, but not what we not want. So there's some good to it. And then mine is helping, like I said, the most with kind of lower ability people. All right, time to validate. So this is where the weird thing comes into play. So this factor score right here, if I run it, error in factor scores, argument F is missing. So what happens is the two packages I need to run in this kind of freak out with the factor score code because they're similar to both packages. So I'm going to run that at the end in another project just to avoid all that going on. I'll show you step by step how to do that. So we'll go back to factor score after everything else. So I'll go over person fit, which is very similar to factor scoring. And there's no errors that come up with that one. But basically, the person fit is similar to factor scoring, which I'll go over in a little, because it's about the pattern of scores overall. And it's individual, like tracking each person's scores and their patterns in the data, their ability metrics. So example number 1 is a person who got every single item wrong. Right here, you can see 0, 0, 0, 0, 0, number 1. And we can look at their LZ for their interpretation here, for their like ability of that person. But most of the information you want to look at is going to be that factor score we're going to go over in a bit. And here we can look at our item fit. So down here we see that. So basically this is the chi-squared statistic. Very large samples can bias it. So we usually look at those difficulty and discrimination to make the ultimate decision factor that we talked about earlier. But chi-square can be a good validation thing. All this stuff, right? The factor scoring, the person fit, and the item fit are more extra stuff to validate our model and use some other statistics to be like, okay, yes, we did make good decisions. These have multiple statistics showing that this is a good item, right? So the item fit, take it with a grain of salt. Large sample sizes can bias it to make it significant. And here we want something that is not significant. So a chi-square that's not significant means it's a good item. If it's significant, it means it's a bad item. And obviously, like we said, the sample size biases it, and you need a big sample size for IRT. So keep that in mind, and that's why you focus on difficulty and discrimination, but it can provide additional evidence. So here we see item 1, despite the large sample size, like it's a good item. Despite the large sample size, chi-square says, hey, item 4, good item. Item 6, hey, good item. And item 8, hey, good item. So it's another way to further validate those items, to have like multiple statistics saying, hey, it's a good item. Now I'm going to go over what I did with the factor score. So to get to this point, I would copy all of my code, theoretically, and this is also teaching how to do a project. So you'd go here, you'd hit new project and create new project. However, I already have this set up, so I'm going to go to fix it. Right now I'm in AMIO, but I'm going to go to fix it. Save, did I not? Oh, okay. Boo, boo. Here we go. So I would just copy, paste the code, which I already did. But what we'll do is, I'll just do all of it in front of you. So we've got this code here, yay. Now the problem was, the reason we do a new project is it takes out all the other saved issues that could cause an error. So we're going to take out the psych package and the unit dimensionality test, because that's what was causing the error. So we have everything here. And just go ahead and run everything to the factor score. Boop, boop, boop. Look at there, and whoop, there we go. See, it ran this time. So what are these factor scores? This goes over every combination of responses possible. We find out if you scroll here, you can see that there are 65 types of responses that happened in this data set. And you can go down and validate the model with each individual item, kind of see like and you can just get more information about these, right? These types of responses, these 65 combinations of types of responses within the data set. So an example of what this can tell us, right? So number 1, and it can also be good for like if you want to look at someone who got everything wrong, everything right, like what are those combinations and what are those people, to learn more about what those people are like. So number 1 is a combination that happens a lot where every single item is wrong. Now, what happens in those combinations where every item is wrong? What can we predict about that combination of a person. So we predicted that 5 people would get everything wrong. Oh, sorry. Yes. We predicted, got that wrong. Expect right here is what we predict. We predicted that this model predicts that 3.3% will get it wrong, right? But we observed that 5 people got everything wrong in this data set. And then right here, we've got ability score, Z1. So this is basically going to tell us where they would fall in here, right? So someone that got everything wrong would have an ability score of almost -2. So they'd be like here, which the test information captures, right? So that's really useful because you can learn like, okay, so someone with a low ability score is here and they get no items. Maybe someone with 100, right? We could go find, see if there's someone that got everything right, for example, right? There was, we observed that 24 people did it and we predicted 25. So that one was more close, right? And they would have an ability score of 1.425. They're like here. So if you got everything right, this is your predicted ability score. So it's useful information like that. So you can kind of learn a little bit about those combinations and how they work. But yeah, that's IRT. And again, factor, person, and item fit raw validation efforts. Make sure to do what I did and set a new project just so you don't get an error code that will happen. I can show you what that error code is really quick. Just so you know what happens if you don't do what I just did. So if you don't do what I just did, and you get here, it'll tell you, boop, error in factor scores, argument F is missing with no default. And what that basically means is there's 2 packages that have been loaded up in this, and it is conflicting with that code. So there you go. That's everything you need to know in IRT.